you can see it's a because in quantum mechanics we have something like tunneling. If I draw the potential, each hydrogen atom has this potential well. Let me try to draw this. I have a hydrogen atom here, and then each one have a potential well which trap bound states. And so now we have one electron in every bound state. Then you say electron cannot move because Pauli exclusion principle, because each orbit can only occupy one electron. Well, that's not quite true. If you have a spinless electron, that will be true. So electron cannot move. But electron carry spin 1/2. Actually, electron can move. Say if this spin up and this one spin down, then electron can tunnel via tunnel to here. So if you say electron cannot move, probably it's not quite right. So it can move. So that's kind of a thinking going into this process. That's how do you understand a material is a metal or insulator? You try to understand if electron can move around or not. So then you say that if electron have a spin 1/2, then it can indeed move. So we cannot say it cannot move. That's not quite right. But you say electron actually cannot move, okay? Because Coulomb interaction. You know, electron have a Coulomb interaction. Putting 2 electrons in the hydrogen atom, electron will be very unhappy. Not because Pauli principle, because Coulomb interaction. So we go back to cannot move conclusion. So electron cannot move due to Coulomb interaction. Okay. So that seems kind of a reasonable picture. So actually, this picture is actually have a famous name called Mott insulator. You say, if electron cannot move due to Coulomb interaction, then we should get insulator, and this insulator is called Mott insulator. Okay. And but if you put a string of gold atoms, or maybe you can put gold atom to form a gold. The gold is conducting, you know. So that's also indicate that this picture that electron cannot move due to Coulomb interaction is not quite right. At least not always right. So because gold, we do have a metal. Gold is a metal. And this kind of argument seems also apply to gold. Okay. So again, we are not sure whether electron can move or not. Despite, you know, in the presence of Coulomb interaction, can electron move? Okay. So what is the thinking? Okay, so let's assume there's no Coulomb interaction. Let's consider more carefully how electron moves. Okay. And so let's consider just 2 hydrogen atoms without Coulomb interaction. Okay. And if you ignore no Coulomb interaction, if these 2 atoms are very far apart and ignore the tunneling, you know, what is the energy level of this system? You'll say, okay, this is very simple. We have energy level, you have 2 energy level are degenerate. Because if you put 1 electron, this electron can be here, we have this energy. Or this electron can be here, we have another energy. Okay. But we know that if we have a tunneling, electron can move around, can tunnel through. So electron can tunnel through, the energy level will be modified. It's not too degenerate energy level. And they split. It became 2 energy level. One lower energy, another higher energy. And this energy splitting is associated with a tunneling. And in particular, one energy get lowered, another get raised. So therefore, to understand how much tunneling, how much electron move is to understand this energy splitting. That describe how likely electron want to move. So let's give some estimate. What is this energy level splitting? Okay. You say because tunneling, if without tunneling, suppose this energy level, so this is a classical allowed region. In the classical physics, electron can only move in the classical allowed region. So you can think of the wave function probably something like that. But in quantum mechanics, since you allow tunneling, electron also move in the classically forbidden region. So the wave function would have tails. Okay, so this is psi 1x. This is psi 2x. So it's centered at a different place. Okay. So when things have tails, so say, okay, the overlap of the tail must be the tunneling. So we can compute this overlap of the two-wave function. So this is overlap. So let's assume it's a 1D system. And but in general, this overlap have a phase. In general, this is a complex function. And this is real. Okay, so let's do this. So this is reasonable. This is a probability. This is basically the probability for electron here to be also in here. That's tail wave function overlap. So we see that this overlap tells us the tendency electron to go to another well. So they must be related to this. So this overlap must be related to this. Yes?
In this situation, it's entirely symmetric so far, but where or what causes the separation in energy levels?
I'll come back to this.
Okay.
And here I just want to get some feeling, understanding. So how much electron can go to the other well? But you can see, we feel we need to understand that. But how to quantitatively understand that and describe that, here what we try to do. And so we say, okay, maybe wave function overlap is a quantitative way to describe how much electron like to tunnel through. And that's what should give us this splitting. Okay. But it's almost right. The dimension doesn't work. This is dimensionless. This one have energy. So I'm so much like to put this here, but it's just dimension doesn't work. So there's still something missing here. So this is just example, the physical process. You're going to understand the physical phenomena. And then you try to building things and collect relevant quantities. Once you understand the relevant quantity or relevant picture for this phenomena, then you can put things together and get estimate. Here we are almost there. We got wave function overlap, which seems relevant, but we're still missing a dimension thing. So what is this dimension? Okay. So actually, what we really need is a rate. How much electron want to tunnel through per second. What's the probability per second, some rate. And this actually, so one thing I can interpret this overlap as we can imagine electron just going back and forth in this well classically. So every time it hit this, it has some certain probability to tunnel through. And that probability per hit probably is this one. And but this energy is the probability per second, per unit time. So this energy scale is actually coming from this frequency. The frequency of electron hitting this wall. And certainly this dimension doesn't work, but in quantum mechanics we are allowed to bar h. Well, h bar if you like. Then we have to use omega then. Oh, that matters. 2 pi, we don't care about 2 pi. So, and this one now have right dimension. And so this is what's going to here. Okay. So this is kind of a thought process. So we can using this to estimate, how much electron can go through. And that's give us this. But exactly how you get this, again, the mathematics. Then what happens is following. You can see, suppose we choose this psi1, psi2 as our basis, okay? Then without tunneling, our Hamiltonian is very simple. In this 2-dimensional space, Hamiltonian just 2 by 2 matrix. So it will be the E0, E0, 0, 0, the 2 by 2. So therefore, each of them are eigenstates, okay? And they are same energy, so we have this case. And now with tunneling, okay, so that these two can mix, but this can go here, this can go here. Then 2 by 2 matrix, we just add T here. So T is something tunneling. And T is given by this. So that's why I go through this. It has right dimension because Hamiltonian have dimension of energy. We should put something of dimension energy here. So people usually say this is a hopping amplitude. But actually, it's not really hopping amplitude. It's have dimension of energy. It's not amplitude. But anyway, people call this T hopping amplitude. But it have a dimension of energy. And how to estimate this hopping amplitude? Well, this is the formula. Wave function overlap and some kind of energy scale, the frequency. Okay. And now things get very quantitative. So once we have this Hamiltonian, we finish the physics. Next we do math. We just diagonalize Hamiltonian and just get whatever energy level you get. And from here, we see that if I diagonalize Hamiltonian, then this Hamiltonian is equivalent to 2 energy level. One go lower, one go up. Just like this picture. That's how I get this picture. The hopping just make one lower or make another higher, and you get energy level splitting. And the one with the lower energy, if I plug in, you see that the eigenvector is 1 over square root 2 psi1 minus psi2. And this one with higher energy is 1 over square root 2 psi1 plus. Just math, just do the math, then you get this picture. That doesn't look right. Because what do you mean by minus? I thought plus should have a lower energy. We know that the ground state wave function should not have a pulse. It's if it's a plus, then the picture is this wave function have a picture of this under this. Yeah, that's have no zeros. So that looks like a lower energy one because in one-dimensional system we have a theorem. The ground state have no zeros. And the minus one actually have a wave function is this and goes through 0. So it have a node. Okay. How to solve this problem? Very simple. We just add a minus sign here. Yeah. And that's another point. If a wave function overlap is positive, and then we should have a minus sign here. Okay. So So therefore, so that's the picture. For the two-way function overlap is positive, we have a minus sign here. That is a little bit counterintuitive. And and that's it. So therefore, this is so this is just a very, very basic picture of the hopping between two sites. Okay. And now let's come back to this my first question: why some material is metal, some material is insulating? And then come to this. You can see the tendency of the hopping between two sites is controlled by this so-called hopping amplitude. That tells you how much electron to hop. And this hopping can reduce energy. You can see it can lower the energy by T, or by absolute value of T, whatever. Can lower energy. So that means electron want to hop. This can lower the energy. But however, if you include Coulomb interaction, the Coulomb interaction seems to try to block electron to hop. It's like a blocking. If electron hop to here, it costs more energy. So interaction try to block hopping. But tunneling try to make electron hop. It's a competition. So whether a material is insulating or conducting depends on which one wins. So to compare the two, we should compare this hopping T with Coulomb energy. If T is much bigger than Coulomb energy, then this tendency of hopping can overwhelm this Coulomb interaction. The electron just hop like a free electron. Then we get metal. However, if a Coulomb interaction much stronger, overwhelm this tendency of hopping, then this Coulomb blocking dominates. Then we get insulator. They ask in real material, which one wins? Actually, if you do the very naive estimate, these two have same order magnitude. The Coulomb interaction and the hopping have the same order magnitude. But on the hand, sometimes one wins, sometimes other wins. So that's why we have both material insulator and yes.
How important are spin effects, like alignment versus anti-alignment, in relation to everything else?
Spin effect is important, but here we try to say that because of spin, the metal is a material is more likely to become a metal because the blocking due to Pauli principle is not there. If its blocking is due to Pauli principle, then the hopping cannot win. That is a principle. We cannot violate the principle. But if it's blocking due to Coulomb interaction, then that's a competition between two energy scales. And actually, that's my key point here. We can analyze to estimate this energy scale of interaction with Coulomb interaction and the hopping. Compare these two, then you can get insulator metal. So that's kind of basic picture. However, in the rest of the week, we'll assume that the hopping always wins and the Coulomb interaction is weak. So we're basically using free electron picture. And but there are material where Coulomb interaction wins, and you get insulator. Many antiferromagnetic material belong to this. Okay. So now let's just ignore the Coulomb interaction, and we try to understand quantitatively just due to hopping. If electron can hop around, and so you get the metal, the things can conduct. But now we want to develop a more quantitative theory. How electron moves in such a strange metal. It's not in free space. We have a periodical potential. Electron move under influence of periodic potential. So how to understand the behavior of electron in such a situation? So this basically is the main main topic in at least in this week. Okay, so oh my goodness. Okay. So let's consider some simple thing. Okay. Let's consider a 1D system. Okay. But let's start with two sides. They have 1D simple only with two sides. Then what is a hopping Hamiltonian? I already said it's there. Hamiltonian is something. So let's say E0 equal to 0. So just a 0, 0 without hopping. But with hopping, we have a minus t, minus t. So the minus t just so this is picture, just this. Electron can hop from here to here and here to here, back and forth. So this minus t means the electron can hop from here to here, and this one from here to here. So 1 to 1, 1 to 2, 2 to 1, basically just these two major elements. So basically that is another picture, you know. So this is the physical picture. It's very simple. Electron can hop around between two sides. But its mathematical description is this 2x2 matrix. Okay. So let's consider some more general picture. Let's consider a ring with a 4 side. And we again have a picture. We have T. Electron hop in both back and forth. Is T. You know. So that's a picture. And the picture is very easy to draw and easy to think. But the mathematics that we can translate this picture to mathematics. So that's now we have 4x4 Hamiltonian. Again, on-site energy equal to 0, let's assume. If on-site energy is not 0, then I have put some number here. That's without hopping, what is the energy of electron on per side? But then you have this 1, 2, 3, 4. So you can see now 1 can hop to 2, so that's here, minus t here. And 2 can hop to 1, so that's minus t here. Then next we have a 2 can hop to 3, and 3 can hop to 2. So the 2 can hop to 3, so that's a minus t here. And 3 can hop to 2, that's a minus t here. And similarly, 3 can hop to 4, 4 can hop to 3, that's minus t here. But the 1 cannot hop to 3. So 1 cannot hop to 3, so there's 0 here. So nothing between 1 and 3. And nothing between 2 and 4. But the 1 can hop to 4, and 4 can hop to 1, so there's a minus t here. So that's it, that's it. So this is just an example. You can do that with a 5-side, 100 sides. After all, it's just a big matrix. You know, quantum mechanics is about the big matrix. So we have a picture, you translate the big matrix, you diagonal matrix, you get a spectrum. You get other properties. And so that's basically, so this basically describes electron hopping. And from this big matrix, from this eigenvector, we try to understand the behavior of the electron. Okay. But certainly writing this is kind of tedious. So we write this model is introduce some notation. So this Hamiltonian, we write this as a following. So this ij just means this side. For example, this side is just a 1. You can using this ij to label the sides. So this is it's just the. So therefore, this is the particle hopping Hamiltonian. And the t is hopping amplitude between I side and j side, and we have this. We sum over this ij side. Okay. So this is these two are actually the same. It's just that this is a more compact notation and works for any number of sites. And we don't want to write this big matrix all the time. That's too much. Okay. So So then the next question is that, so what is this, what is the eigenvalue of this Hamiltonian? So big matrix. Usually it's very hard to find eigenvalue of a big matrix. And, but however, here, we have a simpler system because we have translation symmetry. Tij equal to Ti plus n j plus n. So we require that. That is the hopping between 1 and 2 and between 2 and 3, between 3 and 4, they are the same. When you have a translation symmetry, this is easy. It's just a plane wave. You know plane wave's eigenvector and the eigenvalue can be just calculated using plane wave, basically. Yeah. However, without translation symmetry, then this became very, very complicated problem. And usually you have to do numerical calculation to obtain its eigenvalue. And its eigenfunction also very complicated. Actually, this became another very interesting direction in condensed matter physics. This random system. Yeah. And here we just consider a periodic system. So we have this translation symmetry. Okay. And so with the translation symmetry, then we can just we can find this eigenvalue very easily. But how easily? Well, here we really want to use translation symmetry. So therefore, let's introduce a translation operator. T. So translation operator is operator which when you act on I, you get to another side I plus 1. Just translate by one lattice spacing. That's the definition of translation operator. So what is the expression? Well, actually, translation operator have this kind of expression: sum over I. This is the expression of translation operator using Dirac notation. You can check that if you hit this operator with I, then only one term in this summation survived. Let's do this 0. Okay. So only when I equal to I0, we have this non-zero overlap. Then this one, you pick up this term, this becomes I0 plus 1, you see here. Yeah. So this is a translation operator. And also because because my Tij have this property, is translation invariant. So therefore, we can write this as a summation of I and a summation of n Tij, or T, let me see, I plus n I, let me just using this, I plus n I. We can write this way. You know, here we sum over Ij, but here we sum over I and I plus n, but this I and n just we sum independently. It's the same summation, just writing in a different form. But the translation invariant means that this Ti plus n and I only depend on n, do not depend on I. It's only depend on how long you hop. That does not depend on where you start hopping. Okay. So therefore, this actually is a Tn. Tn means how many steps you hop. For nearest neighbor, n just equal to plus or minus 1, etc. Now, because T do not depend on I, so this summation of I can go into this. Then you get a Tn sum over I. Yes?
I'm just confused because in your Hamiltonian matrices you have negative T, but in the equation you wrote there isn't a negative?
Okay, I put the minus sign here. But here we have Tij. So maybe I think it's better to put a minus sign here. Yeah, thank you. Yeah, to be consistent. Yeah. So let's put a minus sign here. Okay. And so the point you can see, what is this? Well, this quantity is a translation operator n times. It's translated n times. So then if n is -1, that means it's the inverse n times. Yeah. Okay. So we managed to write Hamiltonian as a minus sum over n, Tn, and the translation operator n times. So Hamiltonian is a function of translation operator. So this is no surprise because we have translation invariance. So for the translation invariant system, Hamiltonian always have this behavior, have this form. Okay, so now we can use the eigenvector of a translation operator to diagonalize Hamiltonian. That's the main thing. You know, if Hamiltonian is a translation invariant, we know the translation operator and Hamiltonian would share the same common eigenvectors. Here I just show that explicitly. Hamiltonian is a function for translation operator. So every eigenvector of a translation operator is also eigenvector of Hamiltonian. Then what is eigenvector of a translation operator? Well, eigenvector of translation operator is a plane wave. We can write down this K. Okay, when you see the K means plane wave. It's a bad notation. Maybe. So this is a plane wave. Okay. This I, J, K all mean different things, unfortunately. I is not the label. I is this imaginary number. This K is not label. K actually is a label. But the K is a wave vector. And this J is my original label, which is label sites. So it's a very bad notation, but anyway. N is the total number of sites. So this is just a normalization factor. N is the total number of sites. N is total number of sites. So this will be normalized. And this one actually is eigenstates of a translation operator. You can check that when you hit T to K. Okay? Then this J get translated by 1. So that became now J is translated by 1. You know, this operator hit this J, it just increase J by 1. And then we can redo the summation, just shift J by 1. So we repeat J by J minus 1. So this 1 cancel out, and so this becomes J minus 1. So this will still have the same summation domain variable. And then at the end, we get this 1 over square root of n e to the minus I k. This shift. And then we get this same summation j e to I k j j. And so the eigenvalue actually is e to the minus k. Because this summation gave us back k, but with this actual eigenvalue. So in general, we have this t to the n k equal to the e to the minus I k n k. So this is a general results if you shift n times. So there, from here, we can immediately see that if Hamiltonian act on this k, this k is eigenvector of a translation operator, but it's also eigenvector of energy. And we can just replace this, because whenever t hit on k, you get some number out. So you can replace this t by its eigenvalue. So there, when h hit to the k, what you get is you get the k, and the minus sum over n Tn. The eigenvalue is e to the minus I kn, and which is epsilon k. We see that epsilon k equal to minus sum over n Tn e to the I minus kn. So that's in one dimension. Yeah, this is pretty quick, but basically it tells us that we can using this we can using the plane wave. The plane wave is eigenstates, and you can using plane wave to obtain the energy eigenstates, and this is eigenvalue. It's a function of k. K is a wave vector. Okay, so there are several things. This looks complex. You know, how come energy to be complex? Okay, and certainly there's something I kind of gloss over. That is, I cannot put arbitrary t here. No, I have to put some right t. Yes. Yeah, we have to put a right t to make Hamiltonian Hermitian. If you're stuck in arbitrary complex number t here, the Hamiltonian is not Hermitian. Okay. So what kind of t should we put here so that Hamiltonian is Hermitian? Well, actually, it's already here. If this direction t, this direction should be t star. If t is complex, the hopping backwards should be t star. Certainly, if t is real, it doesn't matter. T and t is not the same. If t is complex, I have to be careful. Hopping forward is t, hopping backwards is t star. So if t is complex, I should put the t star here. And I think t star here. Yeah. And then that's related to the following. You can see Tij is hopping in one direction, Tji is hopping backwards. And these two cannot be independent. So we have this relation, Tij equal to Tji star. So this relation guarantees this hopping Hamiltonian to be complex and legal. So therefore, when you have a complex hopping, things are a little bit more complicated. So the hopping should satisfy this condition. If you say that if a hopping amplitude have this condition, then that means translating to here, that means Tn. Remember, n is like I minus j. There's difference. Tn should be equal to t minus n star. You know, Tn is a hopping by n step in one direction. Minus n will be backwards n step. So they should have this relation. Now, once we realize Tn and t minus n are complex conjugate, then obvious this expression is always real. It works. Yeah. So therefore this so this is okay, but we do need this condition. This eigenvalue always real, because real energy. Okay, any question here? Yeah. And so this is another thing. What is this? You say, oh, this is the energy for k. But you say, I'm not looking for a function. I'm looking for a bunch of numbers. Because we have a matrix. Its eigenvalue is a bunch of numbers. And here, after some magic, you give me a function. You know, it's not what I'm asking for. I ask a bunch of numbers. But you give me a function. So what's going on? Yeah. So actually, again, there's something I kind of gloss over. You know, when you have this, when you have a periodic system on the ring, so it's like this. So we have a ring with n side. Now, not 4 side, but we have n side. this is not always legal. The k has to be quantized. K cannot be any real number, any wave vector. K cannot be any wave vector. If a k is any wave vector, this is illegal. The quantization condition is that this function, this is the wave, this is the wave function. This wave function should be periodic on the ring. So that means we should have this condition: e to the I k j equal to e to the I k j plus n. It should be periodic. If each ring, have n sides, then it has to satisfy this condition. Now this is back to the notion of Brownian zone and this quantization wave vector. And this really requires that k is equal to, is quantized, is an integer times let me see, 2 pi over n. Yeah. K is that. Only those k are legal. So k are not a real number, it's some discrete value. So using this discrete value, then we can just plug those legal k here. We get a bunch of numbers. And this bunch of number is actually the eigenvalue we are looking for. Okay. But there's still something wrong. Because this integer is an integer. We have n by n matrix, If we have n side, we have n by n matrix. We only ask for n numbers, and we get infinite. And so there's another subtlety here, is that not only k is quantized, k is redundant. Means that the two different values of k actually describe the same wave function. That looks strange, because k is a wave vector. How come two wave vectors describe the same thing? Well, on the lattice, that is actually the case. You can easily see that if k and if k prime equal to k plus, say, 2 pi times n. No, not 2 pi times n. 2 pi. I'm sorry. If k differ by 2 pi, they are the same wave function. Because e to the I k prime as function, so let's consider as function of j, as function of j, this k prime is this. And another function of j with k is e to the I k j. J is integer. These two wave functions are actually the same, because if plug this k prime into k plus 2 pi here, just e to the I k plus 2 pi j. Because j is integer, so therefore 2 pi times j and with I is 1, so these two wave functions are the same. Okay, so this actually, I think the last week you already seen this. This gives you a notion for Brownian zone. So two things that the whole space is a compact. We get a big circle with n sides. This compactness of a space tell us the k is quantized. K cannot have arbitrary value. The fact that the space is discrete, that the space only contains those discrete points, tell us the k is a compact. K cannot be arbitrarily large. So there's a dual. You can see, if x is compact, that means k is quantized. If x is quantized, means x only have discrete point, means k is compact. K cannot be arbitrarily large. And so 2k differ by 2 pi is the same point. So then actually it works, because if the integer run from 0 to n, 0 and n is the same thing, because 0 and n just differ by 2 pi. So this integer equal to 0, integer equal to n really describe the same plane wave. And so therefore the way to label this k is a Brownian zone. So we have a k, we have a 0, we have a 2 pi. Then those are allowed value. And this satisfy this quantization condition. And then everything fit. So finally you get everything right. That is the discrete k inside this Brownian zone. And we just have n such, which has n such k actually. Inside each Brownian zone we just have n such k. And this n different value for discrete k plugging here gives us n different value of energy. That is the eigenvalue of this n by n matrix. So finally understand everything. So now let's do some plotting. Okay. So let's assume this T1 equal to T minus 1 equal to 1. Okay. Or maybe equal to T, so let's say. The rest other T just equal to 0. Then we just plug in here. We just plug in here. Where are we plugging? Sorry, plug in here. Then from here you can see that epsilon k is just equal to this T minus T e to the I k plus e to the minus I k. So one contribution from n, one contribution from minus n. Yeah, n equal to 1, n equal to minus 1. Yeah. So this gives us a minus 2t cosine k. Yeah. So this is this energy. And if you plot it, so usually we plot not from 0 to 2 pi, we plot from minus pi to pi to plus pi. Then this energy just goes like this. Yeah. So that's why we only plot energy in the Brownian zone. It's a periodic, outside the Brownian zone, it actually is repeat the same thing. And so this is the energy spectrum, or energy band we call, in a one-dimensional crystal, but with only nearest neighbor hopping. We just have this nearest neighbor hopping. Yes?
So you call first the Brillouin zone to be between 0 and pi, right? No, you're saying that the Brillouin zone is between minus pi and pi.
Yeah, that's your choice. The key point is that we want to find the k which label every state. We can choose from 0 to 2 pi, those k label distinct states. But from minus pi to pi, those k also label distinct states. So that's your choice. Yeah. And this is using minus pi to pi is more symmetric. Yeah. So we usually use this way. Yes.
Isn't there also some sort of redundancy in this sense that almost all the information is contained in half the Brillouin zone? Because you could just take that part, and if you reflect it around, you get the same thing. So there's that information.
Yeah, very good point. Okay, very good point. And so actually, what you talk about is not redundancy, but the symmetry. So now let's because the question, let's bring this up. You can see if I only plot, if you have this eigenfunction, I just plot this, I can keep plotting. This is a periodic function. Then you'll say, okay, this k and this k have same energy. And that looks like a symmetry. The two things have the same energy, like a symmetry. And here I want to emphasize that's not the right way to think about this. Actually, this k and this k have same energy not because there's symmetry, because redundancy. This label and this label actually label exactly the same wave function. We have bad labeling. We try to using k to label wave function, but our label is bad. It's not one-to-one. Many different K label same wave function. Of course, same wave function always have a same energy. So we are happy to see, yeah, they do have same energy, but this is redundancy. But these 2 points have the same energy. K minus K have same energy. It's a symmetry. And that's a physical property. That is, for some special reason, these 2 different states, the K minus K are different. Usually, different states have different energy, usually. But if your Hamiltonian are very special, you have symmetry, the different states have a same energy. And here the special thing is that our T is real. If T is real, it have this K minus K symmetry. And so, but this is a symmetry, not redundancy. So this K and this minus K are different states, but different states have the same energy. And so when we draw it, we do not want to draw same state twice. So that's why we limit ourselves in the Boolean zone. But these 2 different states have same energy. Their symmetry property want to show that, yes, we have beautiful symmetry. Yes.
When you're plotting this dispersion relation, it's in the limit where I have infinite number of particles, right? Because, I mean, this is a continuous...
Actually, so you have to interpret this as the K are discrete. Yeah. So I'm glad you bring this out. So those are really just this point. I'm sorry. Yeah. So when you look at, because you'll see this curve a lot in the physics in the condensed matter books. But every time you see this you should imagine actually those have those tiny points, because if your sample is a finite, certainly if your sample truly infinite, they will become continuous line. But if your sample have a periodic condition is finite, those are just all these discrete points. Okay, so this is the picture. Okay, and so certainly this can be generalized to higher dimension, and so. These are not working very well. Okay, let me do this. Okay. I hear something coming down. Okay. And so the thing what I just did is a 1 dimension. So but 2 dimension, unfortunately, what I write is hiding. But anyway, 2 dimension is actually you just do the vector. So let's just quickly write down something for 2 dimension. It just put all index as a vector, you know, and then this those labeling also as a vector. You know, just instead of using an integer, we can use an integer vector to label sites. Okay, and so again we can write if you have a translation symmetry, that means this as a vector. You know, we have this property, and we call this equal to ij. Uh-oh.
Don't use automatic, better use manual.
Okay,
yes, so
I see.
You can help the control of the
Okay.
This is the oldest one, this is medium, this is
Sure.
the...
Okay. Okay, at least this is the one I'm writing on. Okay, so this is once we have this, again, we can write this as a t, you know, I. Let me see. T using j plus n tj. And so it's maybe let's not write it here right now. So therefore, this is so this one can be also written as a minus Tn This n is how much you hop. And then you have this hopping operator by n. Okay. So maybe just this way. So here I'm very, very, very quick. So this hopping operator by n side is really just equal to this I, but I plus n. Yeah. Okay. Just make everything what I write, put the arrow on top. Then you get a higher dimensional version of this one-dimensional thing. And then you can using this then you can put a vector here. Then you get a wave function, but in a high dimensional plane wave function. And plug this wave function to here, we find the energy as a k vector just equal to minus t. Let me see. There's a minus here. Yeah, actually, this is the main thing I want to have. Yeah. So if you go to higher dimension, you just get that. Okay. So let me just give you one example of a higher dimension. That's say we have this we have a square lattice, and then we have this we have the hopping in x direction. We have a t back and forth, also t. You know, they're supposed to be real. And in y direction also we have a t backwards, also real. So that means the following. That means t when n equal to x, that's equal to t. And when n equal to minus x, that's also equal to t. That means the hopping forward and backwards in x direction is t. And similarly for y, if n hopping in y direction, that's equal to t. And if n equal to minus y, that's also t. That means in y direction, up and down is t. Imagine you can modify this. So maybe this t and this t are different. This is tx, this is ty. And also, if t is complex, this can be t, this can be t star. You can see. You can make hopping more general. Actually, I won't come back to this. If t is complex, you no longer have a k minus k symmetry. You can check. If t is complex, you no longer have symmetry. So k minus k are not really the same. Yeah. And but for this simple case, then you can just plug into here. So that means this term would for this special case, then the epsilon k will be this. Actually, we have summation. This sum will contain 4 terms: n equal to x, n equal to minus x, n equal to y, n equal to minus y. If n equal to x, this will be equal to minus I kx. Minus x will be plus kx. So this term will just a minus t. We have e to the minus I kx plus e to the minus I kx, but with minus sign, and plus e to the minus I ky, and plus e to the minus I ky with minus sign. Okay? So just 4 terms, because we have a 4 hopping, backwards, forward, 4 hopping. Combine this together, very simple, minus 2t cosine kx plus cosine ky. So that is a dispersion relation. So how to plot it? So one way to plot is the following. Again, the Brownian zone, because we have same thing. Kx, ky only in the range plus minus pi. So the Brownian zone is just a minus pi to plus pi. Here is a minus pi to plus pi. Those kx, ky label distinct wave function. Otherwise, it would be redundancy. Okay. And it's better to do some contour plot. You know, if you do the contour plot, you can see that the minimum energy at the center, just like the one behind this blackboard. At k to 0, we have lowest energy. And then energy would increase. So then the contour, if you do contour plot, will be something like this. But then when the energy became 0, actually the contour became a square. That's interesting. And then the contour will become something like that. You can imagine that's how this energy spectrum looks like. Okay. So this is and one thing I want to emphasize that in these two cases, the energy is reasonable in the following sense, because the lowest energy in both cases. So in the 1D case, let me write down. That's a minus 2t cosine k. In the lowest energy means k to 0 is the lowest. If I expand near k to 0, what we get is a minus 2t some constant term plus k squared plus t times k squared. Yeah, that's what we get. So what? Just the expansion. Well, here is I want to rewrite this. This term can be written as a h bar squared k squared divided by, I put h bar squared downstairs divided by t. Then there's a 2 here. 2 here. Maybe I can put it by 2t here. Maybe let me do this. Okay, so this term can be written as this. Why I do this? Because h bar k squared is a momentum, is a p. So I write this as a form of a p squared over 2m, where m is this combination, string combination, h bar squared over 2t. That's m. Okay. So that means near the bottom of band. Remember, in 1 dimension, we have a band. Near bottom band, it's like a parabolic energy momentum relation. And we have some mass here. This curvature, the square mass. So we can imagine at least one particle near bottom band, it may behave like an ordinary particle in free space, but with different mass. This mass of a particle are not just a particle in free space. It's some kind of something associated with hopping. So this hopping gives us this mass. Okay. So similarly, if you expand in 2 dimensions, expand near 0, you get similar results. Because near this point, again, the energy is a k squared. You can convert k back to momentum. So energy is proportional to p squared. And this coefficient in front of p squared tells you inverse mass. But again, this inverse mass are very different from the free space electron mass. Just totally different mass, controlled by the hopping. Yeah. And so here we get the first lesson is that actually, when you really do this, we find the electron moving in the periodic potential kind of just like an electron moving in the free space. And but with a modified mass, with a very different mass. And so actually this became a dominant picture. So if you calculate this electron effective mass, then we can basically using our picture of a free space to imagine how electrons move around in the lattice, just with different mass. Okay. So this is the first approximation. and which not always true. And actually, in this week, this first order approximation actually basically correct, but there's some subtleties not being captured. There's some other effect. So in this week, we'll try to capture this the other lattice effect, not just modify the electron mass, but there's other lattice effect. And one of the lattice effect, you'll find sometimes the electron can even be massless, like a Dirac fermion. And so that's something we'll discuss, I think, in section today. But that situation can happen if you have some more complicated hopping. That's where I will discuss. So what is this more complicated hopping? There's one thing there's one simplification I did. You can see in one dimension, for example, there's a unit cell. I assume there's a one side per unit cell. There could be a situation like this. You could have a two side per unit cell. Or in general, you can have an n side per unit cell. Then that's much more complicated hopping. So we'll come to that point. You know, when you have this multi-side per unit cell, what happens? And it turns out that like a graphene happen to have a two side per unit cell. You know, graphene is a carbon atom from a honeycomb lattice. If you really draw a unit cell carefully, you can count. Actually, there's two carbon atoms per unit cell. So actually, graphene belongs to this more complicated case. And when that happens, sometimes you can have a so-called Dirac fermion. It's like a massless fermion. Okay, but I will not talk about that. But I will just discuss a general formulation for this. The general formulation actually is not difficult. The first we need to label this. So each unit cell labeled by, so this is unit cell, this is another unit cell, etc. So each unit cell labeled by I. But however, the side inside unit cell are labeled by A. So here we need to have a pair of labeling, I and A, to label every site. I now no longer label site. I label which unit cell. And the A label site inside each unit cell. Okay. This sounds very simple, but actually that's the start of every physics research. You need to find the right label. And if you don't know how to label things, you cannot even write down anything on the paper. Actually, that's the most difficult part, actually, to find the right label. Indeed, I'm not joking. And so once you find the right label, then you can write things on the paper, and you can do computation. You know, that's actually what Newton faced when he write down his equation motion. Because there's no differential equation at the time. There's no calculus at the time. You know, how do you write down an equation motion, a curve, you know? You have to invent derivatives. You have to invent symbols to describe things. And here we do some little bit invention, invention of pair of index to label the sites. But once we find a proper label, then we can go on to write down something on the paper or on blackboard. So once we do this, we get a TAB IJ. That's it. So basically, the meaning is very simple. This TAB IJ is again hopping. It's a hopping amplitude. So it doesn't have a dimensional energy. It's hop from a site labeled by J and B to a site labeled by I and A. Just that, just like before. But however, the translation symmetry we only have translation symmetry as this. So we have this translation symmetry. Again, this helping amplitude only depends on the difference between I and j. And here you can imagine I and j can be vectors to go to higher dimensional situation. Okay. So, and that's it. So that's a Hamiltonian. And but how do I find eigenvalues? Okay, you can say because we have a translation symmetry, we want to use plane wave. And here we are using K space. Here rather than writing this in terms of translation operator, so I try to using so-called plane wave basis. I'll use plane wave basis. When you write this Hamiltonian using plane wave basis, it will be simpler. Then we can find eigenvalue easily. So that's another way to do this. And the plane wave basis is the following. It's a K A is equal to 1 over n square root of n sum over I e to the I k dot j. So this is a, sorry, A, yeah. We just keep A index intact. We just do the Fourier transformation on the I index or j index.
Sum over j, right?
Sorry, sum over j, yes. Yeah, because this I is taken as a unit of imaginary number. Okay. And so then that's okay. And then there's inverse Fourier transformation is given by this j a yeah. So this is the inverse Fourier transformation. Okay. And so there's a difference by sign. And it's kind of strange to say, what do you mean by sum over k? K is a wave vector. Here j is integer. But here k is a wave vector. Wave vectors are discrete, as I mentioned there. The wave vector actually, this k actually equal to integer times 2 pi over n. So we sum over discrete wave vector. So that's what it usually means. K is a wave vector, but we sum over this discrete wave vector. Okay, so this is just a formula for the Fourier transformation and the inverse Fourier transformation. It's just a plane wave basis. You can see this I basis is a real space basis. Now I'm using wave vector basis, and these two formulas just relate the relation between two bases. Okay. Then we insist using the new basis to write down this Hamiltonian. Because we have a phase for translation invariant Hamiltonian, if using K basis, it will be simpler. So whenever you see a translation invariant system, you just write them in K basis, and you get simpler results. Okay. So we just let's just do the math. We need the middle board. Okay, let's just do the math. So this is maybe just a. Let me do this. J prime, and P. Okay, so this is our Hamiltonian with a minus sign. Okay, So what you do actually is pretty simple. We just plug this in. You know, J is here. Just plug this in. Okay. It's a very messy, certainly. Oh, certainly there's a minus sign. There's 1 over n. There's 2 factor 1 over n squared, so give us 1 over n. Okay, then we have summation of j prime. But we also have summation of k prime, because when we plug this in, we have to name these two dummy index differently. One is k, another we have to name it as k prime. Okay, so then we have this j prime ab. Okay, then this then there's a factor from here is that it's e to the minus k. Let me see what is my notation. K. Yeah, k j and e to the I k prime j prime. Then this is a j. Sorry, this is the k a k prime b. Yeah. Okay, basically, this term and this term will sum over k, give us this j term. So, and then this term times this term will sum over k prime, give us j prime term. That's how things fit together. And there's a few factors. It's 1 over n just makes things work. Okay. And so what? Then we need to sum over this j prime. And here the key point is that we sum over j and we sum over j and the j prime minus j. Instead of sum over j prime, we sum over j and their difference. That would be okay. So therefore, we can replace this as a j and n. N is their difference. In this case, this number only depends on their difference. So this just became only depend on n. This became very important because translation invariant. This only depends on n. So that's why we do this. Okay. Then this j prime became j plus n. So this became j plus n. Okay. Then you can see that things now became better because only these two terms depend on j. Yes?
One question. You're considering sum over nearest neighbors only or in general?
In general, because here the j prime can have a bigger difference. So n tells this difference. So then if we only have nearest neighbor, n will be very simple, just plus minus 1. But n is plus minus 2 will be second neighbor and etc. That'll be underhopping. Yeah.
The other thing is the A and B, of course there's an implicit sum over there.
A and B here I just keep in. I don't touch A and B.
They just interact within the cell. They don't interact with neighboring cells.
They can go beyond the cells. So actually, that's a very, very good question. That is, if j prime is the same, then this TAB describes hopping within the cell. However, if j prime are different, this TAB describes hopping from A site in one cell to the B site in another cell. So actually, this is a very general. They kind of capture everything, all possibility. But that's a very good question. Yeah. Okay. So here the key point is that if you sum over j, this term will be 0 if k not equal to k prime. Because the oscillatory. The oscillator test cancel sum to 0. Only when k equal to k prime, the summation of j survives. And that's typical for Fourier transformation, an inverse Fourier transformation. So because of this, we can immediately simplify. Because sum over j make k equal to k prime. So we can drop the prime. And we don't need to do the sum. And then these two terms cancel out. And this j term cancel out. And the j over the summation is done. And then we don't have 1 over n. Because if k equal to j, then there's n terms. So this n term, they all equal to 1. So n terms sum equal to 1. Let's give us cancel the 1 with n. Anyway, so that then I can rewrite this. This immediately became quite simple. N and k, and just e to the I k, sorry, Tn ab e to the I k n and k kb. And that's it. So I want to write this further. Let me write this in 2 steps. Sum over k ab. I'm sorry, I forgot to say. This repeated a and repeated b are assumed to be summed. So let's do it like this. So, and so this is the, let me write this mk ab ka kb, where this mk is a matrix with a major element ab. That's equal to sum over n, and that's the t, n ab, and e to the I k n. So we have 2 formulas, basically. Okay, so let me just say a little bit more. So here we sum over n. So sum over given the hopping. So this is almost like a Fourier transformation of a hopping range. You know, this is a plain way you do the Fourier transformation of hopping range. Then you get some matrix. So TAB is a matrix. You get another matrix of if treat AB as matrix element. Then you get another matrix which is a function of K. And once you know this, you can plug it into here. Yes, this is still pretty messy. Well, not that messy. The key point is I can see here in this expression, K is fixed. Only A and B get mixed up. K is the same. That means this Hamiltonian do not mix different K. That makes things much simpler. Because in the original Hamiltonian, you can see J is mixed, and B is A and B are mixed. The both index are mixed. So after all this Fourier transformation, we find the first index, this wave vector, is unmixed. So it's block. This Hamiltonian don't change K. So therefore, this Hamiltonian have a form. It's a block diagonalized for each K. For each vector K, we get a block of described by AB. So therefore, this Hamiltonian, the K space, actually is a sum, direct sum of, say, MK1 AB. So there's a matrix. Then there's a matrix of MK2. So let's drop the AB. And then MK3. You know, remember K are all discrete value. For every discrete value, you can put this block here, but all other are 0. There's nothing mixing different K. And that's the key. So this Hamiltonian became block diagonalized. So to really obtain the eigenvalue of this Hamiltonian, we just need to fix every K and diagonalize this finite dimensional matrix. If you have a 2-side per unit cell, this will be 2x2 matrix. If you have a 3-side per unit cell, it will be 3x3 matrix. And for the graphene, we have a 2-side per unit cell. So that's 2x2 matrix. You know, physics can do one thing, that's diagonalize 2x2 matrix. so that's okay. 3x3 will be too difficult. And so that's it. Basically, that's how we do it. So now using this, we can handle the multi-side problem. And using last maybe 1 minute, let's just okay. Let's just describe one system. Just using one example to illustrate this. And so again, let's go to picture. The example we're going to have is a square lattice. So that's a side. So there's a 2 side per square, so that's 2 by 2 problem. And then the hopping is that we have a t in xy direction. But we also have a hopping between these 2 sides, t prime. So that's a picture. This picture is very easy to draw. You see which side have a hopping, how they hop. Then from picture to mass, next thing is, what is the mass? Well, mass is this TAB ij. Or more precisely, TABN, And that's a mass. So we need to go translate this picture into this mathematical expression. Once we do the translation, then once we know this, then we can just plug in here to get this matrix as function of k. Then down a 2 by 2 matrix for every k, then we are done. Then we get all the eigenvalues. Okay. So the difficult part actually is this translation from picture to TAB. Well, so let's label this is a 1, this is a 2. Okay. So then we see that there is a tx equal to, let me just draw the describe results. It's a minus t and a ty 0 also equal to minus t. Actually, plus minus x is the same thing. And so here, this AB index is here, I write as 2 by 2 matrix. Okay. And then you have a T0 equal to T prime, T prime. This may be too quick, but let me explain. Actually, it's not too bad. So T plus minus x equal to minus T, that means this T actually is a 1, 1 index. So here is A equal to 1, B equal to 1. So that's a 1, 1 index. So that means we have hopping from 1 in the first unit cell to the 1 of next unit cell, but differ by x. In these 2 unit cells shift by x. So that's why we have a 1, 1 we have here. This you have 0 here because we don't have a hopping from 2 of first unit cell to the 2 of second unit cell. We don't have that hopping. Yeah, this hopping is not there. So this is a similarly between 2 unit cell. We don't have this 2 to this hopping. This is a 1 unit cell. This is another unit cell. You can see from 2 of the first unit cell to the 1 of the second unit cell, we have nothing there. So this equal to 0. And similarly, this equal to 0. Then similarly, that is from 1 of a first unit cell to the 1 of a unit cell differed by y is there. That's a t. So that ty. The unit cell differed by y, but from 1, 1, you have this t. Yeah. The minus y is similar. But t prime, what is t prime? But t prime is hopping from 1 to 2, but within the 1 unit cell. You can see. The unit cell label don't change. It's within 1 unit cell. And so that's T0 is this. Yes?
So where are we considering just like the one particle in the vertex can hop to the center of the plaquette in just one direction? I mean, I have 4, let's say, for a given vertex, I have 4 points here, right?
Yeah.
We're just considering this hopping to.
Yeah, we assume, but certainly, if you add this,
Yeah.
you can certainly add this. Yeah, when you add this, you can see this T double prime. This T double prime will appear as a 1 to 2, but will differ by unit cell. So that will be appear as this element and this element, but they are a bit different.
But why would they be different? I mean, why would they be like a T double prime and not the T prime?
No, here I just assume.
Okay.
I assume there's only hopping this way. There's no other hopping. This is an assumption of a problem. Yeah. Maybe for some reason these two sides are very close. But just using this example to illustrate how do you obtain this this quantity from the picture to this mass. Yeah. And but once you get this mass, then it's very simple. We just plug into here. You know, n can be plus minus 1 in x direction or plus minus 1 in y direction. So again, this is 2 dimensions, so I have to put a vector here, you know. And so at the end of this, we get this mk equal to this minus 2t cosine kx plus cosine ky. And then we have a minus t prime here and 0 here. You can remember, minus t prime have no k dependence because this n equal to 0. Something onside, n equal to 0, no k dependence. And t have a kx, ky dependence because t describe something between different unit cell. So there's some finite range hopping. When your hopping have a range, then you have a k dependence. Yeah. And so when you diagonalize this Hamiltonian, this Hamiltonian is easy to diagonalize. You can diagonalize Hamiltonian and get this eigenvalue. Yeah. And the spectrum to plot is so the spectrum is a little bit complicated. Let's just plot the spectrum kx equal to ky along this kx equal to ky line. If t prime equals 0, the spectrum is very easy to plot. Just like this. If kx equals ky, just plot it. Just 2 cosine just add up. It's just like this. And if t prime equals 0, then this 0 just means there's another band. It's 0, just like this. It's 0. So this is a picture for t prime equals to 0. If t prime not equal to 0, well, this crossing is resolved by t prime. You know, at the crossing point, so spectrum looks like this. And this, yeah, you can see. You get a band, dispersive band, then almost flat here, then dispersive again. Then almost flat here, then this anti-crossing became dispersive, then almost flat here. And so that's a spectrum looks like this. And the bottom of the first band is quadratic, like something with the effective mass. The bottom of the second band almost flat, something with a very heavy mass. The flat means the mass is very big. Yeah. So this is a picture for the second. And so in the session you will see another example of this two-band hopping, and you'll see very different dispersion relation. And they make something like a Dirac-Kramian. Okay, I will end here. And so in the next class, my main question is the following: is that you know, how do you know this particle behave like a particle with a mass? You know, here I just say, well, from the dispersion relation of a band bottom, you say, okay, it's like a particle with a mass. That sounds reasonable. but do you believe me? You know, how do you know the equation motion behave like Newton's equation? The mass gets modified. Yeah, curvature is modified. But why we can still use Newton's equation motion? You know, even worse, suppose you have some strange system where the dispersion range looks like this. You know, it's a mess. Or equation or some dispersion like this. And the bottom is like a k to the 4th. You know, those situations where when Newton's picture may not work. But the particle electron will still move around. But which law do they obey? That's the question. And do they still obey Newton's law? Or we have modified Newton's law? It turns out that we have a modified Newton's law here. But we need to find a way to derive an equation motion, how electron moves. Yeah. Okay, I will stop here.